right, this lesson is all about matrix multiplication. So number 1, a teacher assigns final grades based on a weighted system. Students are graded on unit assessments, a semester project, and the final exam, each with a different weight. The matrices given below represent the weights for each kind of work and the grades for 2 students, Oscar and Reagan. What are the final grades for each student? So we can see for the weighting, we have a unit weight of 0.5, a project weight of 0.3, and a final weight of 0.2, meaning like your final exam. All right, and then we have 2 columns under grades, one for Oscar and one for Reagan. So the way that your final grade would work is that you would take 0.5 times your unit grade, add that to 0.3 times your project grade, and then add that to 0.2 times your final exam grade. So in the case of Oscar, if we were going to figure out Oscar's grade, we know that we have this matrix that is 0.5, 0.3, 0.2. And we are going to multiply that times the column that represents Oscar. Now, if you notice, unit is in the first position here, and unit is in the first position here. Project is in the second position, third position, third position. So we are going to end up taking the first number in the first row times the first number in the first column. So we have 0.5 times 90, and that represents the unit percentage times the unit grade. All right, this first one. Then we have the 0.3 in the second position. We're going to take that times the 95 in this second position. So we're going to add 0.3 times 95 plus, and then same thing, third position times third position, 0.2 times 75, and that gets us 88.5. All right, now we're going to do the same thing for Reagan. So we have the same percentages, the 0.5, the 0.3, the 0.2, but her grades are different. She has an 80 for the unit, a 70 for the project, and an 85 for her final semester test grade. So we have 0.5 times 80 plus 0.3 times 70 plus 0.2 times 85, which gives us 78. Now, notice that this was first column or first row times first column. So when we make this matrix, that 88.5 is going to go in the first row, first column. All right, then we had first row times second column. That number is going to go in the first row in the second column. And so now that we have our matrix, we have a 1 by 2. Now, you can only multiply matrices where the first one has the same number of columns as the second one has rows. So like if you had a 3 by 2 and a 2 by 4, this has 2 columns and this has 2 rows. So we can multiply these two together, and in the end, the result will be a 3 by 4. So the columns in the first matrix have to match the rows in the second matrix, and that's because you do column and row, column and row, column and row. All right, so number 2. Below we have some square matrices. That means that they have the same number of rows as they have columns. And they want to know if the equations down here are true and what conclusions we can make about commutative and distributive properties when multiplying square matrices. So they want to know if we take A times B, is that going to equal B times A? So let's start with A times B. So I know that A is -2, 1, -1, 0. and B is -1, -5, 0, and 4. All right, so when we multiply these, remember, we are going to start off by doing first row, first column. So we do -2 times -1. So first number in the column, or row, and first number in the column. Then we do plus, and we're going to go second number, second number. So 1 times 0. So that was the first row, first column. So this is going to go in the first row, first column. All right, then we're going to leave a little bit of space because we're going to do the first row with the second column. So that will be in the first row, second column. So we have -2 times -5, and then 1 times 4. Now we're going to do second row, first column. So -1 times -1 plus, and then 0 times 0. Now we do second row, second column. So that's going to go in the second row, second column. -1 times -5 plus 0 times 4. Now you can either, put each of these in the calculator or do them by hand. I'm just going to do them by hand. All right, so we have 2 plus 0. That gives us 2. All right, then we do 10 plus 4. That gives us 14. 1 plus 0 gives us 1. And 5 plus 0 gives us 5. Notice you had a 2 by 2 and a 2 by 2, so columns matched rows, and you ended up with a 2 by 2 in the end. All right, now we're going to do B times A and see if we get the same thing. So B is -1, -5, 0, 4. A is -2, 1, -1, 0. And we're going to start off by doing first row, first column. So we have -1 times -2 plus -5 times -1. Now we do first row, second column. -1 times 1 plus -5 times 0. Second row, first column. 0 times -2 plus 4 times -1. And second row, second column, 0 times 1 plus 4 times 0. That gives us 2 plus 5, which is 7. -1 plus 0 is -1. 0 plus -4 is -4. And 0 plus 0 is 0. Now, when I did A times B, I ended up with 2, 14, 1, 5. When I did B times A, I ended up with 7, -1, -4, and 0. So this is not commutative, meaning we cannot multiply it one way and multiply it the other way and get the same thing. It might work out every now and then, depending on what you're multiplying by, but it is not commutative, all right? It's kind of like if we did 2 times 3, that's 6, but so is 3 times 2. That's also 6. That's commutative, but multiplying matrices is not commutative. All right, so let's think about, is it distributive? If I took A times A plus B, and I distributed and did A times A and A times B and added those together, would it be the same? So we're going to start off with A times A plus B. So I'm going to write down my matrices just as this is written. So A is -2, 1, -1, 0, times A, which is -2, 1, -1, 0, plus B, which is -1, -5, 0, and 4. So you do your order of operations here, which means you're going to have to add the two things that are in the parentheses. So I'm going to add these two matrices together. I have a -2 plus -1 is -3. 1 plus -5 is -4. -1 plus 0 is -1. And 0 plus 4 is 4. And then I'm taking that times A on the outside. So first row, first column, -2 times -3 plus 1 times -1. First row, second column, -2 times -4 plus 1 times 4. Second row, first column, -1 times -3 plus 0 times -1. And second row, second column, -1 times -4 plus 0 times 4. That's going to give us 6 minus 1, which is 5. 8 plus 4, which is 12. 3 plus 0 is 3, and 4 plus 0 is 4. All right, now we're going to do A times A plus A times B, where we have distributed this matrix here. So let's start off with A times A. So A is -2, 1, -1, 0, -2, 1, -1, 0, plus A times B. So -2, 1, -1, 0, times B, which is -1, -5, 0, 4. All right, so if we multiply A times A, we get -2 times -2 plus 1 times -1. -2 times 1 plus 1 times 0. -1 times -2 plus 0 times -1. And -1 times 1 plus 0 times 0. I'm running out of room, so I have -2 times -2 is 4, minus 1 is 3. -2 plus 0 is -2. 2 plus 0 is 2, and -1 plus 0 is -1. I'm going to be adding that to what I get over here. So we have -2 times -1 plus 1 times 0. -2 times -5 plus 1 times 4. -1 times -1 plus 0 times 0. -1 times -5 plus 0 times 4. That's going to give us 2, 14, 1, and 5. And if I add those together, 3 plus 2 is 5. -2 plus 14 is 12. 2 plus 1 is 3, and -1 plus 5 is 4. And that is exactly what we got when we did A times A plus B. So, distributive property is true. All right, so we're going to find the product here. I have a 3 by 3 and a 3 by 3. So columns match rows, and we're going to end up with a 3 by 3. So I'm taking I times A. So we're going to start with first row, first column, and then do first row, second column, first row, third column, and then we'll do second row, first column, second row, second column, second row, third column. All right, so we have 1 times 1 plus 0 times -4 plus 0 times 9. All right, moving to the second position, we have 1 times -3 plus 0 times 5 plus 0 times negative 7. Moving to the third position, 1 times 2 plus 0 times negative 6 plus 0 times 8. Then we're going to do the second row, positions 1, 2, and 3, so on and so forth. Keep in mind, though, that these represent your columns from the second, all right, all of these second numbers. So since you know that, you could just say, okay, I know this is going to be times 1 times negative 4 times 9. I know this is going to be times negative 3 times 5 times negative 7 because those numbers aren't changing in those rows. So you know that this is 0 plus, and then you have a 1 plus, and then you have 0. And it's the same here. So 0, 1, 0, 0, 1, 0, 2, negative 6, 8. All right, and then your third column, you know you have 0, 0, 1, 0, 0, 1, 0, 0, 1, and then your column numbers are going to stay the same. All right, it just makes it a little bit easier when you have a lot of them to do, if you can do it that way. All right, so if I add all of these up, okay, these first ones are going to be 0, 0, so this is just 1. All right, these second ones right here, 1 times negative 3 is negative 3. Again, 0, 0, so my third is 2. All right, then you're going to get negative 4, 5, negative 6, 9, negative 7, 8, and this should look familiar to you because it is matrix A. All right, so this should teach us a valuable lesson. Do you see how this this matrix right here has this diagonal row of ones? This is called the identity matrix. Its main diagonal is made up of ones, and then every other number is 0. Now, they are also squares. All right, so identity matrices are always square, and they always have a 1 as each of the elements in your main diagonal, and then zeros for all other elements. All right, so write that down somewhere. Identity matrices are always square with a 1 as each element of the main diagonal and zeros for all other elements. All right, so always square. Always square. So when I multiply by the identity matrix, it doesn't matter which way I multiply by, but I'm multiplying by it here, I'm still going to get A, which is 1, negative 3, 2, negative 4, 5, negative 6, 9, negative 7, and 8. So if I multiply by an identity matrix, I get the same matrix. Okay? All right, so you need to make sure that you can identify an identity matrix. So this is a 2 by 2. This is a 2 by 2. Since my columns match my rows, I'm going to end up with a 2 by 2. Notice this is a square. It has a main diagonal of 1s, and every other number is a 0. That means if I multiply by this, I am going to get the matrix that I am multiplying by. Essentially, it's like multiplying by 1. So again, if you look on number 6, diagonal row of 1s, 0 zeros for the other numbers. So I'm going to get 5, 0, 8, 2. You could sit there and multiply them out, but this is going to save you some time if you can identify those identity matrices. All right, number 7, we don't have one of those, but we do have a 2 by 2 and a 2 by 2. I can multiply them together, and that's going to give me a 2 by 2. So first row, first column, 3 times negative 2 plus 0 times 3. First row, second column, 3 times 1 plus 0 times negative 4. Again, remember, these numbers are going to stay the same because you're just going to be multiplying by those columns, those same columns. All right, so I have negative 1 and -2, -1, and -2. But if you want to just say -1 times -2, -2 times 3, you get the same thing. So if it confuses you to do that, then just go on about your day doing it the normal way. All right, so I have -6 plus 0 is -6. 3 plus 0 is 3. 2 minus 6 is -4. And -1 and +8 make 7. And I did end up with a 2 by 2. Here I have a 2 by 3 times a 3 by 1. Columns match rows. I should end up with a 2 by 1. So we'll do first row, first column. So we have 10 times 50 plus 15 times 14 plus 12 times 38. Then we'll do second row, first column. 7 times 50 plus 11 times 14 plus 20 times 38. So if you do the top row, you get 1166. The bottom row is 1264. And we did end up with a 2 row, 1 column.